Now we are going to continue with this idea of doing each one of the elements and the constitutive relationships of each. And I would like to see that we take each one of those that you see here, the I, the C, the R elements, the TF, and the GYs, uh, one by one, so that we understand them in all the energy domains and understand all the equations that they have. Because what after all what we are doing right now is to try to represent them in the bond graph form, and we try to represent them also on the block diagram form. So any way you see it, you should be able to recognize the element and what it does, because each one of these has a specific purpose on a system, and it does different things. Like, for example, the I element stores kinetic energy, the C element stores potential energy, the R element dissipates energy, and the other two are conservative elements that transform energy. So each of these functions on a system influences the way the system behaves completely. So what we're going to see now is we're going to see uh, the, how each one of those behaves. So I think that the easiest one to take on first is going to be the R element, which is will introduce us in a simple way to the subject. So here I'm going to put the R element. So we're going to call the resistive element. Okay. How would we represent it in the bond graph way? As you can see, I told you that we need to do it consistently across the board. So the R element is this. The R element, you can represent it like this. Something is happening. It's not, it doesn't flow in here. Did I actually overload the system? I don't know. When you have an element like this, you have two possibilities. You have this kind of representation, or you can have this kind of representation like this. So let's just sorry, let's see, we have, I put it on the wrong, because normal elements have the power into them, and so it's in here too. So you have in the bond graph model, either could be like this or like this. So we could just put it consistently with the same color as we did in the previous slide. In this right here, we're gonna say bond graph. I don't know why is the computer, there's a delay in there, but how come something is funny about this? Because it's as if the eraser is turned on. Yeah, but what we were doing is over here. See? Okay, well, we'll survive with this. So this is your bond graph model. We were going to put your block diagram, and then in here we are going to put the, let's call it the equation, or the, yeah, or constitutive relationship. You know, this would be, it is a better term, you're gonna call it constitutive relation. I don't know why there is this delay, but there is. In here, you see the way the block diagram is like you have this R element, and let's see, we had it with black over here, like here. See what is going out of the R element. In here you have the effort variable that is going out, and what is coming in is the flow variable. On this other one, the flow is going out and the effort is coming in. What does it mean? In here it means that when you draw this in the block diagram form, it says this is the R element, but we could actually use the representation the same way that Simulink has it. So let's do that, because that way it'll be totally consistent with what we're doing. I am going to put the, let's see, how do we, what will be the best way? Yeah, if this is the R element and it comes in here like this and goes out like that, in this case the what goes out is the variable E, what comes in is the variable F. Sometimes we represent this in the in another way, like, let me just try this, because you're going to see also a lot this way. If you, it's the same thing but drawn a little differently. What comes in here is F, and what goes out is E. See, and this is R. So I don't want you to get confused. These two are the same thing. But what you are seeing here is that the variable effort is equal to R times the variable flow. So you see this constitutive relation, this equation, corresponds to this block diagrams or to this bond graph model. It is a total direct relationship. If you have it like this, I'll do the same thing here. So that you will see a both representation. If you have this kind of causal mark in the other way, of this is called the causality, this crossbar. What goes into here is the E variable, and what goes out of this is the flow variable. See, it's totally the reverse of this. So you have to be careful here. And on this other one, you are saying that F is equal to 1 over R times E. So this is 1 over R. And so if you have it like this, it means that the effort is what comes in, but what goes out is the flow, like that. Okay? And this is your constitutive relationship. So what I would like is to conclude that the way it represents the constitutive law directly affects the symbol here or the way it is on the block diagram. There is a direct relationship between those two. So it is going to completely represent this element in the bond graph way or in the block diagram or in the mathematical way, depending on the input and depending on the output. So I think what I would like to do next is just very briefly put the examples that we have in there in the different energy domains. Let's just maybe draw a line on this one. I'll draw a line over here. We had first on the in the electrical domain, you have it like this. This is a R element like this, and it's as if, if you put the voltage source like this. Let's just, for the sake of example, do it this way. You have a current I. For this kind of element in the electrical domain, you will have that the voltage of the resistor is equal to I times R. This is something that we do know. On the mechanical domain, and if you have a damper like this, and you apply the forces in here, you will know that F is equal to the value of the times the velocity. This is the value of the of the damper. If you go on to the hydraulic domain, you have a very similar situation, or this probably is not the best example. I think let me erase this one because I don't like this. Why don't we just do this? This is gonna be like a valve. See, so we have in here a pipe like this, and we put a valve in here with a like that. See, then we know that you have pressure, and then you have flow in here. This is saying that the pressure, let's do this too, is equal to the constant in the UCP for this bar times the volume flow rate Q. And finally, if you put it in a rotational system, this is like you have a torsional damper like this, where you have some angular velocity in here, And what you are saying is that the torque is equal, the opposing torque is B in rotation times the angular velocity. So you see, this is your physical system, and then you have the bond graph, this is the block diagram, and the constitutive equations. So I'll just put a title in here, in here that says physical system, and with this we'll see. Hold on, I think I made a mistake in here. This is your physical system, and let's just put a nice title. This is the physical system. Okay, with this we will take a break and then we'll continue with the other elements.